glass of beer or wine. I'll try and make it interesting for you. Let me just get a gauge on who here is making hardware or is familiar with using hardware. And what about software? In particular, who programs in C, for example? Okay, got a good mix. What I want to try and do is buzz through these slides quite quickly and show you some of the code there. We've got quite a few people who can understand that. The reason I put hardware for software engineers here is this is a slightly different way of looking at things. It kind of extends what a microcontroller can do without the complications of things like VHDL and Verilog, etc., or HDL. So what I'm going to do is just move through some of these quickly. And what I want to talk about here is concurrency or parallelism. And down at this end of the table we have the basic microcontrollers or microprocessors. But this is great for all sorts of fairly basic applications. Some examples here: simple state machines, PWM, RC servos, for example, LED driving, lighting, low frequency ADCs. Anything that's open loop that doesn't require very, very quick response times. Temperature control, PIDs, logging, monitoring, sensoring and measuring. And we've seen quite a bit of measurement going on with the Internet of Things, for example. Then right at the other end, we've got the really complex real-time devices that have to deal with many, many different things. So what's happening at this end is the system somehow is juggling many different tasks, IOs, or closed-loop systems. Applications, things like multi-axis servos, multi-channel communications, things that do 10 serial channels over an Ethernet socket, or applications like a smart grid that may be starring out like Ethernet to a number of low bandwidth ports, compressing them down to one single high bandwidth gigabit or something. Multi-channel audio is very difficult. High rate audio with multi-channels uses up your processing power pretty quickly, particularly if you're doing DSP on the audio in real time. Brushless DC field-oriented control, which is probably the most optimized way of driving brushless DC motors. With this, you're relying on the microcontroller, microprocessor, or FPGA to actually work out where the data is in real time and what the magnetic fields are in order to run it at different speeds in the most efficient manner. That's really important for high efficiency systems, motion control systems. Ultrasound, ultrasonics, again you need the speed. High frequency ADC acquisition, digital signal processing. Real-time closed-loop control, where you have very, very hard deadlines. Things like AVV and EtherCAT, which is very low latency messaging over existing Cat5 type Ethernet cabling. And display driving, and also high-speed USB. So if we look at sequential microcontrollers, they're simple, low cost, it's all in the code. You don't have to know too much hardware. You can just be a software engineer in many cases and write your firmware. But not so fast, Batman. Your normal control loops and configuration for something like a microcontroller is a main, which does the configuration and then runs a kind of tick process normally. You then do all the stuff that you need to do in a hurry in something like an interrupt, and you're reacting to GPIOs, etc. But of course, it's just a serial machine. It's only doing one thing at any one time. So what we have here is your main program starting things off, then you've got a tick routine running, and that is being interrupted as and when things in the outside world requiring attention, etc. And this model works very well. The trouble comes is when you need to service a number of different peripherals, or you've got lots of different things going on, or lots of different closed loops that you have to worry about, that you can't miss, you can't drop. And in this sort of situation, what you end up doing is making this much more complicated because you have interrupts interrupting interrupts. And it gets very, very hairy very quickly. And pretty soon you'll have something that is very difficult to predict and is unlikely to hit your real-time goals. Real-time operating systems do quite a good job of this, but they also sacrifice how quickly something can operate, because they're effectively still slicing the time up into this sort of fashion internally. They're just giving you a standard way to do it. Okay. So if we're looking at Agile Concurrency, again, at this end, we've got our good old microcontroller. At this end, we've got ultimate parallel FPGAs. And the problem with something like an FPGA, although it's a very good solution for some things, it's a very, very complex tool set. Because quite often you're going to find that you're going to need to have a core within that FPGA as well. So you're actually combining a number of disciplines. You're combining, you know, HDL or Verilog VHDL skills, which are very, very different in many cases from the kind of C and software skills. You do find people that do actually do both of these, but it's actually quite a rare combination. So actually getting something working in an agile fashion when it comes to designing an FPGA project is very difficult, and you have very long cycles, development cycles. Whereas we look at this end, and we're looking at the microcontroller, you know, your cycle is as fast as your make command followed by a JTAG or upload, which tends to be a few seconds, quite literally, and it's very small amounts of code. When you're dealing with things like the FPGAs, you have enormous amounts of software that have to run to compile the Verilog, etc., and then set it into the FPGA chip itself, and then it has to run the core, then it has to upload the software as well that you've written the core and have that interact. So you've got a very, very long cycle. It's very difficult. But there is a solution, which is what I want to talk about today, what I call nicely concurrent. And I'm going to talk about a device called the XS1 from a company called XMOS, and I'm going to talk about tools around it and explain why it's different and why it might be a good reason to go in between those two things and get some of the agile benefits. If you remember what we had before, we had a main routine and then a basic tick algorithm that's constantly being interrupted. Well, when you run on something like an XMOS XS1, you have a number of cores. The chip you buy can be bought with a number of different cores built in. So if we look on here, at the top we can say we've got our blue core running 3 tasks, our green core running another 3 tasks, our yellow core running another 3, and a red core running a final 3 different tasks. So in terms of our grayscale of concurrency here, within a core we have tasks which run on the same effective core, and then we have cores running multiple sets of tasks. Some of these tasks can share memory, some of them can't. It depends on the configuration of the chip. But you can always use channels as a communication medium that will always work between any cores. Okay. And this is a message passing system. So you are duplicating the information by moving it. You're not passing things like pointers around. If you're doing memory manipulation, you may be passing pointers around. So what does it provide? Well, it gives you a good scale of concurrency. You can buy an XMOS XS1 chip for about £2, and that will give you 4 cores, and in each of those cores you can run several tasks. Or you can go up to much larger core systems, as I will mention in a second. They have a very fast response time. They have an event-driven model, which is a really good way to program when you're dealing with very complex systems. They are deterministic. That just means predictable, and I'll go into a little bit of that. There's a very agile tool set, comes free of charge, and everything is code, basically. Everything you do on this is code, as you'll see shortly. You don't have to learn peripherals, you actually write peripherals. code is basically your peripheral. So as I said before, looking at the concurrency angle, you've got many tasks per core, up to 16 cores per chip on the new XS1 series that XMOS produce. And there is an older chip called the G4, which actually has 32 cores on it. They also have a Scalable Interconnect, which allows many chips to be put together on the board. Now, what that means is you can actually combine the chips to get as many cores as you want. But the great thing about this is once you started writing your software, you can add in as many cores as you want in order to solve a problem. And then if your problem gets more complex, again, you can add more cores in if you need to do that, and reuse your software. In terms of response time, it's got about a 10 nanosecond resolution, so it's much faster than your average microcontroller. The clock tends to run about 400 or 500 megahertz. You've got up to 93 I/O lanes, and there's different types of chips with different numbers of I/Os. 256 for the old G4 4-core. And every input-output is like a parallel interrupt. So you're not confined to a single sequential interrupt. These can all effectively be treated as interrupts, which gives you untold flexibility in terms of real time. Every ping can generate events, and I'll talk about that. Timers create events. Channels and streams create events. This is where communication between cores happens. And what was introduced recently is interfaces into the language, which is an extension to C, which I will show you, which enables these things to talk to each other safely without you getting into race problems and bound access problems, etc. The deterministic side of this is guaranteed response times for instructions. It's predictable in terms of input and output timings. You've got granular timers and clocks, and you've got clock-accurate simulation. So you can actually simulate and see exactly what your I/Os are doing within the toolkit itself. So you can know predictably that your software will do whatever it needs to do within certain times, given that you can provide the stimulus to test the model. And that simulation is built into the tools. You can use an IDE, which is Eclipse-based, which has all the tools in it. You see a screenshot here showing various different features. This is the xScope, which is a built-in data function that enables you to move data very quickly from your live code back to the host machine so you can see what's happening with the data. Unlike kind of print commands, which are just too slow, they will slow your code down if you use a print command. Shoving the data backwards is a really easy way of doing that. There is also the timing analyzer. I'm not showing it on this picture shot, and that will show you the timing charts for your software. This is called the xScope, by the way, which is just like an oscilloscope. And you've got a simulator as well. The debugging is done by a JTAG, and it works with GDB. Now you can use the command line if you don't want to use a toolkit, and the IDE. So everything is code. No custom peripherals to learn. You don't necessarily have to write this, but if you want SPI or I2C or a UART or ULPI over USB, most of that code's already done anyhow. It's available, download. It's all open source, and I'll talk about the libraries in a sec. Yes, it's all bit banged. But it's not bit banging in the way that you would expect a microcontroller to bit bang. This stuff is running very, very, very quickly. But at 10 nanoseconds resolution, you can actually talk to your Ethernet PHY and keep up. It's very, very fast. One of the other things is you get this kind of modular concurrency. So this piece of software was written by XMOS. It's called StopIP. I think it's actually a very bad name. It doesn't encourage open source development. People get the IP mixed up with proprietary. All of the code, or virtually all of it, there is a few bits of USB code that is proprietary. All of it's on GitHub, and it is open source under a very open license. And they encourage contributions. But what you can do here, what's happening in this window is you can run this software, so you can choose all these components on the left-hand side, You drag them into your application here, and it will tell you exactly what resources are required in terms of timers, clocks, IOs, and cores, etc. So you know what sort of chip you need in order to meet the requirements of this design. That will even turn it into a project as well, if you need to, that you can open in the IDE. So it's a really handy tool. Isn't concurrency really difficult? Isn't it a real bitch in C? Normally it would be. What XMOS did was they didn't just stick to C. They actually went on and added some extensions to C to make the concurrency much easier. The simplest form of this is how you run tasks. By putting them within a par, you can, it turns what would normally be a serial run this, run that into two parallel running tasks. Really is simple. In order to make that possible, they have introduced things called interfaces, which are type-safe inter-task communication protocols and communications. You have timers and ports as well. So if we take, for example, this situation here, my cheapo logic analyzer, I've got 4 logic inputs and a trigger input. I've got 4 dip switches here to set a pattern. I've got a display that is 8 bits wide that I can send numerical information to. So what would that look like in terms of some code? Here. Is it?
Yeah, I have that front.
Okay. Let's have a quick look at this. It looks very much like C. There's a few new important features. Ports are very important. Now, ports are the I/O pins, effectively, but they have a different type of width. So you can have a 1-bit port, which is just 1 bit going on and off, or you can have a 4-bit port, like a nibble. You can have an 8-bit port, you can have a 16-bit port, you can even have a 32-bit port, which is good for writing to memory and things. And you have a number of different ports that overlap each other on the pinouts, depending on which chip that you're using. Here I'm specifying that this is using an in port. So I can actually tell a compiler that this is only ever going to be used as an input. So if I try and use it as an output, it will catch me doing something silly. I could just put port here and use it bidirectionally if I so wished. Clocks, it has a bunch of clock blocks effectively in there. These are used so that you can do synchronous data transfers into and out of the chip. Here I'm combining some ports and clocks together to create an interface. This is my user interface for that display that I'm going to use. And then there's a function down here, which is an interface. So this will be how the tasks communicate. And tasks work with a client and server. There are 2 parts. You've got or more parts. You can have many clients on one server. So in this case, I'm defining an interface called display that responds to these function calls effectively. In this case, it's update, and I send it the count number and the timestamp for the pattern that it's capturing on my logic analyzer that I've got here. I've got another function here, which is get pattern, which enables me to go and receive a new pattern to look for. And I've got a pattern ready signal, which is used to actually tell me when there's a new pattern ready. So if I look at the main program here, so first of all I'm defining that port structure, my UI port structure. And this is the way that these are defined in the headers that you import for the particular chip or the development board that you've got. And then down here we simply run 2 tasks, a display task, we pass it the IDSP interface, which we defined here, And then the capture task, which is doing the logic capture in this case, pass the interface, and then we pass it the input port that it's looking for the signal on, and then the trigger signal port. And if we look at the dirty details of what's going on with these tasks, if we take the display task first, we've got some fairly familiar C things going on here. We're then configuring our clock rate. We're then looking at our setting the clock output here, and then we're starting the clock. We're then using our timer to get a timing marker. And then we're using what's called a select. And this is the way that XC deals with events. This is a bit like a switch. In the switch, you will have an integer or something similar that determines which case that you take. In this case, there is no switch integer. What you have is events bubbling up from the hardware or from the interface. So what it's saying here is if this task is called with the get pattern, this case will run because it's just looping around these selects. And it will read the dip switch settings and return that to the pattern variable. So this is an input from a port command. Here. So it's reading that port, putting it into the pattern variable, and the pattern variable is what's returned from this call. If the display is being updated by the client thread, because this is a server thread, it receives a count and a timestamp. And it checks to see if we're within a certain range, and then it turns the display on. It then sends out the count and then the timestamp to UI data. This is actually quite strange here because you've got a 32-bit integer being sent out here over an 8-bit data. We're using a thing called buffered ports, which it enables you to serialize an 8-bit port with a 32-bit number. It will clock for 8 bytes straight out automatically without us having to do any extra commands. So you can operate at a much higher speed with less interaction. It's a lazy way of doing it. You can think of it like serialization. So it sends out the count and the timestamp to the display for us. Here's a use of a timer. So alternatively, because we're good energy citizens, we're going to put our display to sleep if it's not doing anything for a period of time. Okay, so all it's going to do here, it says when the timer is after a certain time, and that's set to 0 to start with, then it will turn the display enable off, and then it will read a new time, then it will have a delay to that time, so that next time round it will wait until that's gone over. And we've got similar sorts of things going on in the capture task.
That -5 now.
Sorry. Here we've got, it's waiting for the pattern ready signal. It then gets the pattern, and then it waits until there's a triggered signal. So down here, when it gets the trigger signal, because it knows that the triggered pin has changed or toggled, it then takes the timestamp of that, enables a trigger, and then it will start triggering, looking at the logic port input, and every time there's a change on the logic port input, it will then send that to the display update and record all of the occasions where it sees that pattern with the timestamp. And this will run very, very quickly because there's not actually much running in this. Just quickly to finish off, so that's the software and the extensions to see. Back to me, please. I just want to put some information up so that we've got the links.
Looks like it's in the background.
Yeah.
Are you going to put the links?
Beforehand.
going to put them on the. How do you stick them on the website anyway? Yeah.
Yeah.
Oh, no,
xCore is the XMOS community. It's got over 10,000 members. Quite a few of those are spam members, obviously. I took that from the bottom of their current membership. GitHub houses the xCore open source repositories. There's over 100 contributions already, small libraries. And it's waiting for anyone else to contribute. Quick word about the hardware. They have a very good system called slices. So if you look at something like a slice bit, it has a standard peripheral interface. This is one of their high-end development boards. This can sit in 4 different I/O cards. And these guys are real simple. It's using a PCIe edge connector. And those can go straight into this. And you can put in lots of different ones, as well as the debug one, which goes in here. So it's a great modular system. These slices are kind of a standard. It's a weird standard. There is commonality between all the slots, but some of the slots have extra functionality. And you can also daisy chain these boards to add up the cores. This is a 16-core example. They also do a start kit, and we're running the workshop tomorrow. If you come along to the workshop, you'll get one of these to take away. This is a smaller version. The good thing about this is it has a built-in JTAG debugger. Half of the chip is used to JTAG, the other half is used for your application. It has an ADC on it, USB, and it has a slice connector. Again, same sort of thing as this. The only difference is this is a horizontal one. Okay. There are all sorts of slices available that XMOS make and other third-party companies are making as well. This is an Ethernet one, for example. And that's called the slice kit. Any questions? I'm talking out to
yeah, it doesn't matter.
keep looking at your beer and wine.
They're going to be all right. Yeah, questions.
Blinded with science? Must be some questions. Oh no, they're thirsty. Okay, one over there.
How fast does the LLVM compiler run? Is it much faster than PGA?
I wouldn't say it's faster than GCC, they're similar. And it's pretty quick anyhow. The code that you're running is relatively small.
So
You've only got 64K of memory in a single tile chip, so your program's not going to be huge. It's microcontroller at the end of the day, so that is pretty rapid, pretty responsive.
So is it up to you to make sure that you put separate parallel tasks so that your events don't happen on top of other events?
Yeah, I mean, if you take that example, I wonder if I can switch back. Bear with me. Ooh, that's weird. There we go. So if we look at the main, where we're controlling this, I'm saying do these in parallel. What effectively I'm doing here is I'm saying run this on one core and run this on another core. I can put some attributes above this that say combine these two, because these two particular tasks I combine onto a single core and they won't interfere with each other because of the way it's written. Alternatively, you can have what's called a distributable task, and that will run on the core from which it's called from. Okay? So there are different ways. So if you had something repetitive that needed to be called up like a library type thing, where maybe you were mapping out certain algorithms repeatedly, then you'd make it distributable so it could be called from any other function. Whereas things that may be associated with certain ports or inputs and outputs, you want to keep in a certain place.
If you're running two functions in parallel and you want to put a data object in the same data object into both of them, That basically.
There's a very complicated answer to that. Basically, you can do whatever you want. XC itself didn't support pointers until version 13, which is the most recent version, to avoid the problem, so that the compiler could actually see that you're not doing anything stupid. It looks for race conditions, it looks for stupid. In version 13, they introduced pointers, as well as the C unsafe pointer, which it can't make any predictions or promises about. It introduced a couple of new pointers, like movable pointers, task shareable pointers, and basic restrictive pointers that you can't really do much with. So you choose the right one for the task, and it will track your usage. The only one it won't track is the unsafe C. So if you do need to go down and you're pretty sure about what you're doing, you want to use an unsafe C pointer, you can do that. But in all other cases, it will be checking your reads and writes and making sure you don't do anything stupid, create race conditions and that kind of thing. Compiler is very good at looking for those sort of problems.
Pretty clever though.
Yeah. Not all tasks can actually share the same memory as well, because they don't all sit on the same tile if you've got like separate chips. So you want to cluster those on that one where they're sharing memory as well.
Right, one more question. Yeah? No? No, you're done. Right, okay, well, thank you very much, Alan.